To proceed further, we're gonna talk about another important property of convex set. For A and B in Rn, we define the interval AB. Over here, B is excluded. This is the following set. This interval contains all elements of the form lambda A plus 1 minus lambda B, where lambda belongs to the interval 0, 1. Here, 0 is excluded, so it is just the set of all elements of the form lambda A plus 1 minus lambda B, where lambda is strictly greater than 0 and less than or equal to 1. Okay. Note that if lambda is equal to 1 in this convex combination becomes A. And if lambda is equal to 0, this convex combination becomes B. Okay, so here we exclude 0. Therefore, this is the interval AB as well. Okay, in the next lemma, we're gonna show that if omega is a convex set of Rn with a non-empty interior, we can take a point A in the interior of omega, and B is a point in the closure of omega. Then the half open interval AB, where B is excluded, is a subset of the interior of omega. So here, the half open interval AB is a subset of the interior of omega. So this is lemma 1.30 from the textbook. For a convex set, omega of Rn with non-empty interior take A in the interior of omega and B in the closure of omega, then the half open interval AB is a subset of the interior of omega. This condition means that lambda A plus 1 minus lambda B belongs to the interior of omega whenever lambda is strictly greater than 0 and less than or equal to 1. Now, let me go through the proof of this lemma. Okay. So, the main idea of the proof is as follows. We want to show that lambda A plus 1 minus lambda b belongs to the interior of omega. So this is A, this is B, and this is lambda A plus 1 minus lambda B. Okay. In order to do so, we're gonna try to prove that there exists R greater than 0 such that the ball with center at lambda A plus 1 minus lambda B and radius R is a subset of omega. So that's the idea of the proof. Okay. Now, since B belongs to the closure of omega, we have that B belongs to the set omega plus epsilon B, where B is the ball, the open ball with center at the origin and radius 1. So this is just the open unit ball of Rn. So it can be written as the set of all x in Rn, so that a norm of x is strictly less than 1. Here, instead of using the open unit ball, we can also use the closed unit ball. The proof works exactly the same. So, how come this property is true? This property follows from an important property of closure of a set I mentioned earlier. So, because B belongs to the closure of omega, for any epsilon greater than 0, for any epsilon greater than 0, we have that the ball with center at B and radius epsilon intersects the set omega. Okay, but this ball can be written as B plus epsilon times capital B. Over here, capital B again denotes the open unit ball. Okay, so now therefore we can find an element A in this intersection. So then we can find A belongs to this intersection. Okay, so now we have that this intersection is non-empty. So we can find an element A that belongs to this intersection. So then A belongs to B plus epsilon times B, and A belongs to omega. From here we can write B as, so we have that B belongs to A minus epsilon B. Okay, so this is just the same as A plus epsilon times minus B. We can easily see that minus B is equal to B for the open unit ball B. Okay, so this is just A plus epsilon B. Note that this element A is in omega. So this set is a subset of omega plus epsilon B. Okay, so we see that if B is in the closure of omega, then B belongs to omega plus epsilon times B. So the geometric interpretation is that if this is the set omega and B is in the closure of omega, then if we enlarge omega a little bit, then the enlargement here contains B. Okay? Okay, so now we take lambda in this half interval and let x lambda be lambda A plus 1 minus lambda B. Okay? Then we have the following properties. X lambda plus epsilon B is equal to lambda A plus 1 minus lambda B. Here we only replace x lambda by lambda A plus 1 minus lambda B. And then we add epsilon times B. Okay? So this is a subset of lambda A plus 1 minus lambda. Here we have B plus epsilon, omega plus epsilon times B. Okay? We just use this property. Okay? And then over here, we also add epsilon times B. Okay? So now, this is equal to lambda A plus 1 minus lambda omega plus 1 minus lambda epsilon B plus epsilon B. Okay? Now we group this term and this term together to have the following. This is lambda A plus 1 minus lambda omega plus, here we have epsilon, and here we have another epsilon, so we have 2 epsilon minus lambda epsilon B. Okay? So we can write it as lambda A plus 1 minus lambda omega. Here we factor out epsilon, so plus epsilon times 2 minus lambda times B. Okay? So I'm going to rewrite it as lambda A plus epsilon 2 minus lambda B plus 1 minus lambda omega. Here we factor out lambda and have that this is equal to A lambda times A plus epsilon times 2 minus lambda over lambda times B plus 1 minus lambda times omega. Because lambda is strictly greater than 0 and less than or equal to 1, this number here is a positive number. This is a positive real number. Okay? Now, we know that A is in the interior of omega. Then we can choose epsilon sufficiently small so that epsilon times so that A plus epsilon times 2 minus lambda over lambda B is a subset of omega. Okay? Now, since A belongs to the interior of omega, we find epsilon greater than 0 such that A plus epsilon times 2 minus lambda over lambda B is a subset of omega. This set is just the ball with center at A and radius epsilon times 2 minus lambda over lambda. Okay? So we can choose epsilon sufficiently small so that this radius is small, and therefore the ball with center at A and radius epsilon over times 2 minus lambda over lambda is a subset of omega. Okay? So then we have the following. Then x lambda plus epsilon b is a subset of lambda omega plus 1 minus lambda omega because we choose epsilon sufficiently small so that this set is a subset of omega. Therefore, lambda plus epsilon b is a subset of lambda omega plus 1 minus lambda omega because omega is a convex set. This set is a subset of omega by the definition of convexity. Okay? Now, so we have completed the proof that x lambda belongs to the interior of omega because at this point we see that the ball with center at x lambda and radius epsilon is a subset of omega. So this property means that the ball, the open ball with center at x lambda and radius epsilon is a subset of omega. So we have proved that we can find a radius, and the radius here is epsilon, so that the ball with center at x lambda and radius epsilon is a subset of the set omega. So by the definition, x lambda or lambda a plus 1 minus lambda b is an interior point of omega. Okay. Therefore, x lambda belongs to the interior of omega.